in this unit, I'm going to give you the basic notions, the two parameters you care about in code, and then I'm going to present two constructions, kind of the mother of all codes, really, the Reed-Solomon code and the Reed-Muller code. And we are going to continue from there, but these codes are the motivation for algebraic geometry codes. Okay, so what is an error correcting code? So at the end of the day, it's just a map. Let's call it C for code that takes case symbols from some alphabet sigma. Usually it's going to be 0, 1, or a finite field. But, and usually it stretches, you should think of case smaller than n. It stretches the case symbols to some n symbols. So actually any function like that is a code technically. So a code is just a function that looks like that. But you don't care about just a function, you care about the parameters of that function. So in this context, so the distance of the code, that's the definition, is going to be, you're going to look at the two closest outputs of the function. The outputs of the function we are going to call code words. So you're going to look at any two distinct code words, and you're going to check how far away them from each other, okay? Namely, in what metric, what is far away, how many entries you need to change in order to get from one to the other. Like on how many indices they disagree. So that's this distance between these two n strings over sigma, and length n strings over sigma. So this is a number between 0 and n, right? Oh, yeah. And you're going to take the worst case. You're going to choose the closest code words. That's going to be the distance of the code. So the picture is as follows. This is sigma to the k. That's the domain. We are going to think of every element here as a message. I'll say why in a second. So you want to kind of take a length k message and do something with it. So what this code does, it kind of hopefully embed these sigma to the k, size of sigma to the k messages into a larger world, sigma to the n in size. And what you want, or what the distance is, the kind of if you look at the image, right? So maybe this red got here and this blue got here. So what the distance is you look at the two closest image points or code words, and that's the distance. And what you really want is to have a large distance. Okay, you want C to spread these things here as much as it could. Okay, and this distance is called the Hamming distance, by the way, number of disagreements in terms of strings. D is going to denote the distance, and delta is that's kind of going to be the better parameter to work with. It's kind of the normalized distance. It's just D divided by N, just to make it a number between 0 and 1. Okay, so that we can compare codes for different ends easily. Okay, so delta is it's called the relative distance, but it's nothing other than the distance divided by the length of the code word. Now, the rate of the code, we are going to have only two parameters. The other one is the rate. The rate of the code is this quantity, k over n. And what it tries to measure is, right, how much is this new space is bigger than the previous one. But it measures it in this kind of scale of k over n. Okay. So I don't think I have, yeah. So why do we care about code? That's what I didn't, right? So if you want to communicate a message to someone, you want to say to send k bits or k symbols to someone, then if you are just going to send them and there's going to be an error, then the other side won't get what you wanted to say, right? So maybe the channel that you are using is kind of non-ideal. So using code, what you can do is you can first take the message that you want to send, encode it, namely apply C to that message, and you get an element here which is longer. So you need to communicate more, which is bad, but what can you do? And then the point is that now the other person, if he knows the code and if he got the actual code word, then it certainly can get back the message itself. Maybe it takes time, maybe it's hard to invert C, but don't worry about that. But the point is that even if there is an error, or even less than maybe D over 2 errors, then even getting kind of a corrupted code word like that, but not too corrupted, there is a way of understanding, there is a unique way of getting back the original message, right? Because if there are not too many errors, then you're still kind of close to that, closer than you are to any other code word. So you know you're just looking for the code word that is closest to you. Forget about computational stuff, but at least information theoretically, you can search for the code word that is closest to you. You look at that, and then you can invert to get back the message. Okay, so that's why we like codes. They enable us to talk, but actually that's not the only reason we like codes. Codes are useful everywhere, not just for communicating. Okay? Good. So they were introduced by Shannon and Hamming as a way of, of talking over imperfect channels, as I said. And obviously, these two parameters, delta and rho, they are competing parameters, right? Because delta tells you that you want to spread the points farther away from each other. And the rate tells you that you don't have too much space. If the rate is small, you don't have too much space. And is not, if the rate is small, say, right, if the rate is 1/2, then n is just 2k, so you double the number of bits. Right, so when the rate is small, this thing is not too large compared to k. So you want to squeeze a lot of points here, which makes it hard to make them spread apart. So these are competing parameters, and therefore you expect that they can't both be large. I mean, each of them is between 0 and 1, so technically they could get their sum, for example, could get to be at most 2, but it's not true. They are competing parameters, and you can see that from the singleton bound, which is a trivial application of the pigeonhole principle, if you want to look at the proof. And it tells you that the sum of them, which potentially could have been 2, is at most 1, plus 1 over n. But don't worry about that 1 over n. 1 over n, for me, n is going to infinity at some point, so it's at most 1. Okay? So if you want the distance to be 0.5, you can't. You have to double the length of the message. Okay. And after the break, we are going to talk about whether we can actually match the singleton bound. Okay, whether there is a code that, for some rho and deltas, actually we'll do it for any rho and delta, for some rho and deltas achieve this with equality. Okay, and that's going to be the Reed-Solomon code, but we're going to see it after the break. Okay. Right, so before the break, we talked about this kind of barrier. You can't have both rho and delta, like the sum of them, to be larger than 1. By the way, you can also ask, maybe you care more about rho than about delta, and you have like weights here, or you don't have to consider only their sum, per se, but let's just consider the sum here. Can you get equality? And the answer is yes, but for that, and for other reasons, I want to define the notion of a linear code first. So, right, when a code C, right, which is at this point just a function that stretches k symbols to n symbols over the same alphabet, so you can, when this function happens to be such that sigma is a field, usually finite, and C is a linear map, right? Once you have this field, you can talk about linear maps over fields. We call this a linear code. Okay, so linear code is just a linear map, but that assumes from the beginning that sigma is a field. And in such case, of course, the image of this vector space is a vector space, right? It's some subspace of f to the n. And sometimes we refer to this subspace as the code. Sometimes we don't really care about the mapping itself. We just care about what are the code words. For example, the distance and the rate don't depend on the map itself. They only depend on the vector space. Right? You just need to know the code words. You don't need to know how you translated the message to the code words. So sometimes we think of this as the code. Accidentally, that's what's written here. I didn't even see. And what's nice about linear codes, there are more than that, but is that you can write the distance in a slightly kind of simpler way. Instead of taking the minimum between every two distinct code words, because everything is kind of symmetric, and from every point, everything looks like as if you are in every other point, right? If you are in the subspace and you subtract an element from the subspace, you stay in the subspace. So it's really enough to kind of fix, for example, y to be 0. Right? It's enough to consider the distance of any code word, any non-zero code word, any code word that takes as an input a non-zero to the code word corresponding to 0, because if you have a non-zero here, you can just kind of add it here and here, right? Or we subtract it from here to get 0 here and here. So this means that it's enough to consider the distance of a code word C of Z for Z, which is non-zero, to 0. Why to 0? Because what is C of 0? C of 0 is 0, right? It's a linear map. It takes 0 to 0. It's not affine, it's linear. It takes 0 to 0. So if this is Z and this is C of 0, this is 0. And so it's enough to consider only the distance from a code word corresponding to a non-zero message to 0. And that we write like that. So instead of talking about the distance, we are just talking about the Hamming, that's so-called the Hamming weight. So this is the number of non-zero entries in this vector. Okay, so again, because I think this is very simple and I get the sense that I did it wrong. So in a vector space, instead of writing y here, you can just plug a 0 here, because if you want to consider the distance between cx and cy, it's the same as the distance between c of x minus y and c of y minus y, because you just move everything by minus y, by y. And c of x minus y versus c of y minus y, well, this is 0, c of 0. And c of x minus y is just another element, x minus y, just another element in the messages space. So really, it's enough to circle over only all the code words, non-zero code words against the 0 code word. Okay. Well, again, this is the Hamming weight rather than the Hamming distance, which is just the Hamming distance to 0. Okay. And I should say that many, if not like definitely most constructions of code are linear. So it's not like a weird subfamily of codes. It's the subfamily of codes. Okay. Okay, so let me give you one very famous example, the Reed-Solomon code. So in order to describe this code, and that's going to be the code that's going to attain the singleton bound. So what we are going to do is the following. So first of all, it's a linear code. So I'm going to need to walk over a field. And like you gave me maybe k and n or whatever, I'm going to also introduce this q. And I'm going to walk over the field fq. Q is going to be a prime power because, fields are only of sizes that are prime powers, and every prime power has a field of that size. And I'm going to require, though, that, well, k is always smaller or equal than n, right? Because you want to stretch things. But I'm going to assume, and you're going to see why, and that's kind of the point here, and that's going to be the trouble later, that q is at most n. Okay, I need at least, I need to have at least n point, oh, no. I'm going to assume that q is at least n. I need to have I need to have at least n distinct points in the field. Okay, so that's a mistake. K is smaller or equal than n, which is smaller or equal than q. My bad. I just, no. Okay, so with that, what I'm going to do is the following. I'm going to choose, so I'm going to define a code now. So I'm going to choose arbitrarily n points, n distinct points in the field. That's why I need q to be at least n. Okay? And I'm going to define the Reed-Solomon code as a function that takes k fq elements to n fq elements. And the way it's going to do it is as follows. Right? So you give me a message. This is a message. I just wrote the actual symbols of the message. Right? A message is an element in fq to the k. So this is an element in fq and so forth. And the point is, when you want to construct a code, you want to have some structure that will enable you to analyze the code. So the one thing you should always do is you take your message, which is kind of structureless, just a vector, right? It's nothing, just a list. And you want to make something out of it that you can understand. So what Reed-Solomon makes out of the message is a polynomial, a univariate polynomial. So before describing the code itself, let me tell you how Reed-Solomon thinks about the message. So what we are doing is we are going to take this message and think of these symbols as the coefficients of a polynomial. Namely, we are going to define this polynomial f sub a is the message, that's the vector, and that's going to be a univariate polynomial, so f sub a at x, what it's going to do, it's an element here, and what it's going to look like is just this thing, just a0 plus a1x, and so forth. Let's say degree at most k minus 1 polynomial over fq. It could be the zero polynomial, for example, if you got a zero message. But the philosophical thing here is that we took something which has no structure and gave it structure. I mean, we just kind of wrote it like that. If we were not going to do much out of it, then but at least now it's a polynomial, okay? And polynomials have bounds, we can talk about them, we understand them. Strings are strings, okay? Just like a dump in memory or something, it's nothing, just like data. Okay, now, so what we're going to do with this polynomial, so we have this polynomial, and the code, what it's going to do is the following. At the ith entry of the code word, like the output, what we are going to do is you're going to evaluate this polynomial, which encodes the message, at the one or the ith points that we initially kind of specified. Okay, so we take the message, think of it, it's nothing, just thinking. Think of it as a polynomial, and then evaluate the polynomial at these n points that we started with that are independent of the message. They're part of the description of the code. I guess most of you saw that, right? Yeah. But that's crazy. I mean, if you're used to it by now, maybe, but like when I talked with my son, he was 10, about codes, and I told him to do it, he did the right thing. He just kind of like took every symbol and multiplied like a couple of times or something, right? Like repetition code. Now he's better. Now he's doing good. Well, but and I told him, no, you should think of the message of a polynomial of a finite field and evaluate it. That's not the first thing you'll do, right? Okay, so you remember that when you're going to talk about algebraic geometric code. Well, two things. First of all, this is a linear code. It doesn't seem like a linear code because polynomials are not linear. That's kind of the point about them. But it's not about the polynomial being linear, it's about the code being linear. For a code to be linear, what we need to see is that if you take A and a B, then the code word corresponding to A plus the code word corresponding to B is the code word corresponding to the sum, and also multiplication by scalars. And that is true because the code word corresponding to A is going to give you this polynomial f sub A, and then you're going to evaluate it. And the code word corresponding to B will give you another polynomial f sub B, and then you're going to evaluate it. And evaluation is linear, right? fa of p plus fa of p plus fb of p is not, it is fa plus b of p. It's not that fa of p plus fa of q is fa of p plus q, but it's the case that in the subscript you are linear. And again, I feel like overcomplicating things, but it is linear. And the rate of the code by definition is Q over N. I said nothing there. I just reminded you what it is. What do we want to analyze now? The distance, right? The rate is there, obvious, now the distance. And the distance, in order to analyze it, like in algebraic geometric codes, even the rate is hard to analyze. But in here, the rate is kind of by construction. The distance is where we are going to use kind of the structure of the polynomials. And the point is, because it's a linear code, right? You remember that when you're talking about linear code, all you have to do is to consider a lower bound the Hamming weight of a non-zero code word. Namely, by that I mean, you can think of it in two ways. By that I mean, when you apply the code to a non-zero message. Okay? So what we really want to understand is this thing. So this thing here. So you are giving me A, which is non-zero, so a k length k string over fq, which is non-zero, and then you're going to apply Reed-Solomon to it. You're going to have n symbols, and you ask how many of them are non-zero. You want to bound that number from below. Okay, so what we care about is how many non-zero entries do you have in the code word corresponding to A, right? Which is this set, right? You care about what's the size of this set, right? All indices for which, when you evaluate fi at pi, fa, at pi, you get a non-zero element in fq. Because fa of pi is the ith entry of the code word. So, Okay, but here comes the point. A is a non-zero message, which translates to the fact that f sub a is a non-zero polynomial, right? At least one coefficient there is non-zero. Okay, and the fundamental theory of algebra, now that's the tool that we're using, tells us that a polynomial of degree at most k has at most k minus 1 zeros. Or degree at most k minus 1 has most k minus 1 zeros, and fa is indeed a degree at most k minus 1 polynomial by construction, which immediately gives a bound on the number of non-zeros, a lower bound, on the number of non-zeros of the code word, right? Just complementing that to n. So this creature, regardless of a, is at least n minus k plus 1, and the rate is k. So when you add them up and divide by n, you get indeed that rho plus delta is at least 1 plus 1 over n. And because the k plus d is n minus 1, at least n plus 1. Good. So indeed, the Reed-Solomon attains the Gilbert, the singleton bound, and sometimes called the MDS code, maximum distance code, and so forth. But that's a fantastic code. Everyone likes this code. What's the problem with the code? The only thing that you can not like about this code? Right, only the alphabet size. I mean, everything else is perfect. I mean, it actually gives you a code for every row and delta that you want, not just for some row you get. It's like a fantastic code, also very nice and clean and simple and computationally efficient and so forth. But well, okay. But the fact that the alphabet size is large is kind of weird if you think about it, because I mean you want to send a it depends on n. So say you want to send like a book or something, and the book is long, but it doesn't mean that the number of letters has to be as long as the book, right? It's like you have like 26, like 50, I don't know, characters that you care about. They shouldn't increase with the length of the book, right? So it's weird in the communication setting, and it has its own effects on any application that you have. Sometimes it's not a big effect, but sometimes the fact that the code requires the alphabet to be large translates to a loss in parameters and things you do care about, because the alphabet is has some relation to the things that you started with and so forth. Okay, so how can we reduce the field size? Well, there is one way, by the way. It's not the best way. There is one way called code concatenation, that if you study a coding theory course, you see that. It's a way of, now you think of every symbol as maybe in FQ, maybe it's F2 to the 100. So you think of it as a vector of length 100 over F2, and you apply the code like inside the symbols. But then you get also losses. Like you have two codes and you kind of lose because you apply two of them and don't understand the relation between them. So it's one way. The other way, kind of sticking to the algebraic approach, is to work with a bivariate polynomials. Or more precisely, okay, so let's see. So I mean, why did we needed Q to be at least n? Now it's written correctly. Why needed Q to be at least n? Because we needed to have n evaluation points, endpoints at which we evaluate. And we took those points from the field. So we needed the field to be large. Now, what would happen if we're going to evaluate a polynomial, but on a plane? So it's a bivariate polynomial, so not as nice maybe, but you have more points than FQ. You have Q squared points, right? So now the number of points is Q squared, which means that the alphabet size is only square root of n, so good, you gain something. Of course, you can take higher dimensions to get, in m dimensions, you get Q to the m, and therefore Q is n to the 1 over m, so you can go like that. But let's just do the m equals 2 case. So this is definitely a way of staying within this framework and like polynomial evaluations and getting the field size to be smaller. Then let's see what it does. Let's see how it works out. So what we are going to do is the following. So P1 up to Pn, n is Q squared, are going to be the elements in the plane, FQ times FQ. Just naming them like that. And what we are going to now do is, instead of interpreting the message as a univariate polynomial over FQ, we are going to interpret it as a bivariate polynomial over FQ. So you have x and y's, and I'm going to choose it in such a way that's the natural choice, essentially, such that the total degree is at most some number. So xi plus y to the j are the monomials that span your world, and I'm going to choose an r. In a second, we're going to choose the right r, such that I plus j, like the total degree, the degree of x plus the degree of y within the monomial is at most r, or maybe here strictly smaller than r. Okay, so we're going to talk about r in a second, but there is some r. Before r was just k, but now it's something else. And if you took like discrete math 1 or whatever, then you know how many kind of solutions do you have, like to I plus j between 0 and r. It's like strictly smaller than r, it's r plus 1 choose 2, I think. So really what we are doing is I want to relate this to n. So the Reed-Muller code here, what it does, it takes, so related to k. So it takes a string of this length, r plus 1 choose 2 elements of fq, and it's going to stretch them, n is going to be larger. It's going to stretch them to n symbols. And this number is exactly the right number such that we can kind of rearrange the indices so that k, such that they are going to correspond to coefficients of polynomial of degree at most r in total degree. So again, I feel I'm overcomplicating things. So what I'm saying is that before it was very easy because we had a0, a1 up to ak minus 1. So the degree was k minus 1. That's it. Now we are going to have like a string. So it has one index, but I want two indices because I want to form a polynomial. And to form a polynomial, I need to tell you who's the coefficient of x to the I times y to the j. So I need to translate one index to two indices. And if you do that, here you have just one index, and here you have I plus j, I comma j. And what I'm saying is that if you are going to construct in a second polynomials of degree at most r in total degree, then your k, number of indices that you got in the one like dimensional case, is translated to be r plus 1 choose 2. Anyhow, so given A, this string, when we think of it as this two-dimensional string, this A is going to induce this polynomial, f sub A of two variables xy, over this field fq, in the natural way, right? So fa of xy is just this polynomial. Okay, so k is just r plus 1 choose 2, because that's kind of the story I told you for like 2 minutes here. And because I want to bound things from below, and because I'm not mind losing a little bit, it's only a tiny bit, let's call this r squared over 2. I'm just losing by doing that, okay? I want to bound k from below, that's definitely a bound. So this means that the rate rho, right, is k over n. I just want to figure out what's rho and delta. So k is this, rho is k over n, and recall is q squared, the size of the plane. So rho is this thing over n. So actually, I didn't use the fact that it's q squared in this point. So it's r squared over 2n. Right? That's the rate. But I could also written it as r squared over 2q squared, and I'll do that in a second. So that's the bound on the rate. That's actually exactly the rate, and unless plus the little one there. What about the distance? Right? Again, the rate is easy to compute, aside from the little bit of confusion there about the indices. What about the distance? And I just remind you that before we used the fundamental theorem of algebra, right? Polynomial in one variable can't have too many zeros. So what we are going to use here, do you know? Unless you know Reed-Muller, do you know what it is? Okay, and if you do know Reed-Muller, what you're going to use? Schwarzschild, exactly. So Schwarzschild is don't tell him, but it's a hack. It's really just the fundamental theorem of algebra, and just apply it to several dimensions. So the Schwarzschild lemma, what it tells you, maybe I didn't even write, I just wrote by the Schwarzschild lemma. So what it tells you is that if you have a polynomial like ours, in say 2 variables, I can do more, and the total degree, that's why I'm using the total degree. The total degree is at most d, then the number of zeros, unless f is constant, is 0, the number of zeros of f is at most d times q. Okay, so like in the one-dimensional case, you have this, right? And now you win a d but lose a q. I don't know. And when you get more variables, the degree of q gets higher and higher, and your gain gets less and less meaningful because you have a d which is smaller than q, but then the rest of the variables kind of give you q, 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 q. And that's tight, by the way, so you can't improve that, but that's also a one-liner from the fundamental theorem of algebra, which you can do. But the fundamental theorem of algebra is not a one-liner. It's hard if you do it properly. So you needed Gauss like to do it. Right, the bound. That's true. The bound is not hard. Yeah, that's a good point. So the fundamental theorem is difficult, but the bound on the number of roots is not that. Yeah, it's algebraic, very simple. Good. Yeah, right. Okay, but it's still harder than the one-liner here, because that's really just induction. So okay, so let's use it. So by the Schwarz-Zippe lemma, what I'm saying is that, okay, so maybe I skipped too much there. So the total degree is r. What I wrote here as d is actually r. So maybe let me switch that to r. Okay, because this is for distance and for degree, so you need to choose who you like more, who you like distance more. So degree kind of deteriorated to be in r. Okay, so the number of zeros of f is at most this, and in terms of fractions, the fraction of zeros, like the number of zeros compared to the size of the plane, is r over q. Right, so r over q is the normalized version. So the number of non-zeros is 1 minus that, at least. So this means the delta is at least 1 minus r over q, because r over q is a bound from above on the fraction of zeros. Delta is at least that. And if you recall, q is a square root of n. So we have this bound. Or put differently, just rearranging, r is at least 1 minus delta times square root of n. Okay, just to have it like that. And the reason I'm writing it like that, because if you remember from before, we said that rho is at least r squared over 2n. I'm trying to get to a point here. R squared over 2n. Plug in this r here. You'll see the n goes away. It should go away. I mean, it should be a normalized number. And you get 1 minus delta squared over 2, which is roughly half over 2, half minus delta. And it's even larger than that. So as a bound, it's okay. So now the dust has settled, and what you see is that rho plus delta is at least half. Right? It's not 1. Before, I mean, we wanted to go to 1, and it's not 1. It's just a half. And not only that, the rate cannot even be larger than a half. I mean, well, obviously, it's okay, it's implied, but you can't get codes that with rate larger than 1/2 even like that. Kind of the plane has its cost, and you know, you decrease the alphabet size, but at what cost? Do you feel that this is a bad thing? You have to write rho is smaller than half. It means that you have to double the message length, no matter what you want, even if you want tiny distance. You need to double the size of the message. Right. Right. That's true. If it was all the way down to a constant, you know, maybe, but only from n to square root of n. So Riedmuller, actually, it's a great code because codes are more than distance and rate. There are more things to them. For example, this is a locally correctable code, which I'm not going to talk about. It has more. Its extra structure, which costs in terms of parameters, has it actually buys you something which is really interesting. But I'm not going to go there. I think you usually don't even see it in coding theory courses, so I'm definitely not going to go there. I will just say, just for fun, that like 10 years ago, someone suggested, but maybe even before in other communities, suggested that maybe you shouldn't just output the evaluation of f of a at pi as the if symbol. Maybe you should also add 2 other pieces of information at the if symbol. So that's kind of not fair, because the alphabet size now is larger in the output than in the input, but so let's say you're allowed to, the alphabet input is different than the alphabet output size. So let's say you're fine with that, but it turns out that if you're going to add also not just the evaluation of f of a at pi, but the two derivatives with respect to x and y, so we get three symbols now. Turns out, I mean, you output more things, so it looks bad in terms of rate. You talk more, so n increases, k stay fixed. So it seems bad, but it turns out that this the Schwarz-Zippel lemma, when you plug to it and use the right version, more information about the function, you actually gain, and this 1/2 goes to 2/3. And when you add more partial derivatives, like second derivatives and so forth, you can get this close to 1. But then the alphabet size increases also, so it's kind of a game to play there. But these are called the multiplicity codes because they use the multiplicity of the root. I mean, right, the fact that pi is a root of f, which is bad, because this means that f of pi is 0, is one thing. But the fact that both f at pi is 0 and its two fractional derivatives means that pi is a root of multiplicity 2, in a sense. So you get kind of a 0 that you see is actually, or these 3 0 that you see are actually kind of two roots, a multiplicative root in a sense. And it turns out that it outweighs the cost of outputting 3 symbols, maybe surprisingly, and you can do much more than what I'm just saying, okay? I'm just saying that this is the beginning of a whole new world. I'm just talking about a little bit about it. Okay, questions? So that's why I want to talk about on the board when I'm doing the technical parts, because I think that when you do it on the slides, you can get lost more easily. So, okay. So let me now we are going to, in the last 10 minutes or 8 minutes before the break, and by the way, after this break, we are going to only resume in 12:30 because there is something between 12 and 12:30. I'm not exactly sure where and what, but we are going to resume at 12:30. So let me just end in these 10 minutes with something that's kind of non-technical and nice, and finally I'll also be able to talk about algebraic geometry codes in some level. So you can ask the following questions, at least from what we saw so far. You saw that when the field size q is n, you can actually get rho plus delta to be as high as they can be according to the singleton bound. Right, when q is n, rho plus delta can be 1 plus 1 over n, which I'm going to not say anymore. But now when q became square root of n, we couldn't quite do that. And I told you that you can do better, but not quite do that. And then you can ask, okay, so for a given alphabet size q, turns out to be an important parameter. So for a given alphabet size q, what's the best trade-off I can get between rho and delta? Okay, I mean, when q is very large, when q is n, then I can get optimal singleton. But is it like just because we don't know how to construct things, or what's going on there? Like, if I tell you I care about binary codes, q is 2, what can we do? Right? You care about binary codes. If the code is of size 49, like 7 squared, it's fair. What can you do, right? So no one quite knows the answer to that. But what we do know is that we know how to use the probabilistic method in order to prove the existence of codes, as I hinted before, without actually finding them. So they're useless for communication, but at least combinatorially we know what to expect. And an easy instantiation of the probabilistic method, this is called the Gilbert-Warshavov bound, and this is not the actual version. You see, it's an inaccurate version. In a second, I'll show you the accurate one, and then you'll see why I didn't want to show it. But let's look at this one. This is the clean, incorrect version. So essentially what happens is that for a field size q, there is always this loss of 1 over log q. You can't get to 1. I mean, sorry, no. These codes give you a code explicitly that get quite close to 1. Sorry, my bad. And the loss that they have is inverse to the logarithm of the field size. Okay, so there are codes. So singleton is the other way. It's an upper bound. It's a barrier. You can't do too well. The Gilbert-Varshamov is a good bound. Like there exists a code such that, for every row and delta essentially, there exists a code as long as this happens. As long as you're not too greedy and rho plus delta are this shy away from 1. I don't know what you see when you look at this. It's hard to, but I don't like it, okay? Like log Q doesn't make much sense to me because, for example, we know that Q is n, you should get equality, right? When Q is n, you have a code, read Solomon. You don't need neither Gilmore nor Varshamov. You can just construct a code quite easily. I mean, and to get equality, so this, when Q is n, it's certainly not tight, right? That's what I'm saying. It's 1 over log n from tight. And log, it's not that far in, like, this is not a super fast function that in terms of growth. Okay, but any questions about that theorem? Yes. No, it's a better bound. Right, good. So when Q increases, I think of this as a loss. You want to get close to 1. Right, so when Q is larger, you get closer and closer to 1. Right, because you have a minus and 1 over. So when Q is infinity, like everything's good, but when Q is 2, for example, well, I kind of hidden the constants and so forth. But for a constant Q, then you lose this constant, and that constant that you lose is logarithmic in the original constant. Now the point is that I don't know. So maybe this is reality. Like there is a reason why this should be reality. The reason for the log here is because it relates to the kind of you look at kind of balls around the code words. You don't want to have other code words there, and you look you consider the not area. How do they call the inside of a volume? You consider the volume of the ball. Thanks. Because and really, what is the code really? You want to kind of pack these balls that are non-crossing, so that you won't get a code word, an element close to 2 code words. And if you think about the volume, it depends on the entropy, and the entropy is kind of, that's where the log is coming. So that the kind of sphere packing arguments will tell you that this should be the best that you can do. The actual bound is this, and that's why I didn't want to show you like that. So this is the correct version that you don't have to remember any of that, but I'm just saying that it's not that rho plus delta is 1 minus 1 over log Q. It's really the rho plus the Qth entropy function of delta, where this is the function, don't worry about it. So the delta this is the kind of related to the volume of the ball. So you need to somehow, it's not linear in delta, but essentially the same story holds. Some weighted whatever sum between them, you ask how close can it be to 1, and the answer is still, well, there is some universal constant, which I don't remember, divided by log Q. And I think I wasn't there. It was like the 50s and 60s. To my understanding, looking at those books, well, many but not all people thought this is optimal. Okay? Because the probabilistic method is always optimal. Yes.
It's not optimal.
Right. For Q equals n, it's not, but maybe for small q or whatever. Maybe, right. Maybe when Q is large, then the field is so large, there is a structure within the field. But I think that they thought that 1 over log Q, some regime, and actually maybe this fixes what I said about n also. The fact that this is the right bound. כן.
אתה יכול בעצם כשאתה אומר שכל רוב ודלתה, ושיש דוגמה אחת שזה משהו מאוד מוצלח, זה לא אומר שזה לא דוגמה נקרא.
Right. So I think that I'm answering in English. So I think that when people say I believe that, they are allowed to put the quantifiers where that there exists a row such that or whatever. But this is just going to be completely false. So that's fine. So you don't have to. This is completely non-optimal. Like in any sense that you would like. Maybe just I'll say what is true before. I'm not sure where we can. Yeah. So maybe I'll just put this slide and we'll talk about it later. But what we are going to do is to construct a code such that rho plus delta, for every rho and delta essentially, this fact that the delta is smaller than that is fine. Otherwise, this is meaningless. So don't worry about that. So we are going to construct codes for every rho and delta such that their sum now, not the weird combination that happened before, is close to 1, not 1 over logarithmic in Q in gap, but 1 over square root in Q. This is much, much better. And this square root U, this 1/2, is the half in the Riemann hypothesis. Okay? And we also know how to prove that using these techniques, you can't do better. So it's like I don't know if it's optimal. It's actually, you can slightly improve that. We're using AG codes in a different way. But I don't know if it's essentially optimal, but it's essentially optimal within AG codes. And now when you go and come back in half an hour, I'm not sure what weight do you put on the fact that there is a square root here rather than log, but you should put a large weight on it. Okay? I can't stress enough. Good. And these are going to be also explicit codes, right? So it's better than what we don't know how to construct with worse parameters. Okay, so yeah. So let's meet at 12:30 and I'll continue that unit. So the idea is as follows. So in Reed-Muller, what we did is we had this plane, right? So ignore this thing. We had this plane, and then we took a polynomial. That was the message. And I don't know how to imagine it, but it was like a mountain here, right? It was like at every point in the plane, you had a value going like that. It's in FQ, so there's not really an ordering there, but some value. And we evaluated the entire polynomial, got this nice picture here, and we proved using the Schwarzschild that there are not too many zeros, not too many valleys, like the picture. And the polynomials that we used were used, we took the message, we thought of it as a polynomial, and that's where we worked with. Like we thought of the polynomial as things that we evaluate, right? So the idea here would be as follows. So instead of evaluating the polynomial, it's still going to be a polynomial. It's a little bit of a lie. It's actually going to be a rational function. But the polynomial that we're going to evaluate now is not going to be evaluated on the entire plane, but rather it's going to be evaluated on a very carefully chosen subset of the plane. And that subset is going to be the zero set of another polynomial, which has nothing to do with the message. It's part of the code description. Right, so now the code description would be, you're not going to evaluate some polynomial coming from message on the entire plane, but rather on an algebraic curve, namely the zero set of a polynomial which is independent of the message, like a fixed one, smartly chosen fixed polynomial. Namely, you're going to have this polynomial g as part of the description of the code, say by a variate polynomial, and the set over which you are going to evaluate is the zero set of that polynomial, namely all xy in the plane on which g vanishes. That's very different, right? Like in linear system, it doesn't matter. Like the kernel and the image of a linear map are vector spaces. But when you talk about polynomials, there is a big difference between their image and between their zero set. It's a different object. And it turns out that we are not so, turns out that, it's really easy to understand polynomial maps, like, the fundamental theorem of algebra and so forth, but it's really, really hard to understand the zero set of a polynomial. Really, crazily hard. And that's what we're going to do in the code. So, not that hard. And this idea of like restricting your evaluation set of points to a smartly chosen subset that comes from algebraic curve. And of course, I need to tell you what function you evaluate. But essentially polynomials is due to Gopa. So that's what he said. He said you should do that, but then he did more than that. He said, well, Gopa knows these things. He said, by the way, I don't know if he's alive or not yet. I couldn't figure it out yet. Still, every time I'm trying to. His homepage is like updated from like 90 or something. Anyone knows? For fun? No? Okay. So, yeah, so if you're watching, sorry for that. So Gopa knew, as you will know, that a curve has important parameters. Obviously, one of them is how many points you have on the curve, but the other one is the genus, which you can't quite see from a picture. And what he did was to connect the genus and the number of points, these two parameters of a curve, to the two parameters in coding theory, namely distance and rate. That's what we will do. Take these two parameters and translate them to these two parameters. And that then will put us in a position in which we want to find curves with a certain genus to number of points ratio or what, something like that. Okay? Like it will translate the questions from coding theory to questions in algebraic curves. So just for example, so that you'll have something in mind, this is a very nice curve. It's called the Hermitian curve. So what's going on here is that let's say that FQ is not, so let's say that Q is as an even prime power, namely Q can be written as P squared for a prime or a prime power P, but as long as it's even prime power. Once you have that, you can define this nice curve, y to the p plus y minus 6 to the plus 1. I don't know if you recognize this, but this is really the trace, and this is the norm from FQ squared to FQ. This Q is the field size, so it's in FQ by FQ. Sorry, it's FQ by FQ, but it's also FP squared by FP squared. So you have like P to the fourth element or Q squared element in the plane, and this is the curve that you're considering. So you need to kind of take the square root of the size of the field. So that's why I require it to be even. And this is called the Hermitian curve. It's a really nice, important, symmetric blah blah curve. Okay? This turns out not to give you a really good code. Definitely not the one I showed you with 1 minus 1 over square root of Q and so forth. This is a better one. It doesn't look like a polynomial, but you care about the zero set, so you can multiply by that essentially. So this curve is due to Garcia and Stichtenhoff. Stichtenhoff is the author of that paper, the book that I'm referring to. Turns out that using this curve, you can get explicit codes that are optimal, like in the sense that not optimal, in the sense that optimal among AG codes, in the sense that I talked about before. And again, P is like square root of Q. You sometimes have examples with kind of nicer and simpler like this thing. This is essentially an elliptic curve, right? Y squared equals some cubic, we'll talk about that and so forth. You can choose many polynomials or rational functions, and each of them will give you a construction of a code and so forth. A question, maybe? So maybe a bit more about it before moving to the more technical, still informal part. So actually, I kind of cheated. I'm not going to just consider curves in the plane, because the plane doesn't have too many points there, like only Q squared. Like I want to decouple the number of points that you have in the code from the field size. So I will need to kind of consider higher dimensional spaces. For example, you consider like the cube, right? So the cube is you can do a Reed-Muller version of the cube, of course, but here I'm talking about, let's say you're looking at the cube, not the plane, FQ cube. And then maybe a curve would be, a curve that we'll use, it will be something like the zero set of so this set, like you have this algebraic relation between X and Y. So that's kind of, in a sense, reduce the dimension by 1. And an algebraic, maybe the same algebraic relation between Y and Z, reducing the dimension in an informal way by another one, so you get a one-dimensional thing, right? You can imagine it's a curve rather than a surface, which is two-dimensional. Right, like in linear algebra, you have two linear constraints, so you get dimension.
Like small Q plane, I think it can be like a bit large.
The Q itself?
Power of like
right. No, large. Good. So the way exactly. So it's going to be kind of log n or something, because I kind of think of Q as a constant in my mind, and I do want to have n points. Like at the end, that's where I'm going to evaluate the code. So I need n points. And only when that free becomes a log n, maybe to the base q, I have the cube itself, like the n-dimensional cube itself has n points in it. I need it to be log n dimensional. And I'm only taking a curve inside it. So definitely I need more than log n dimension. So yeah, so this free is going to be usually like logarithmic in n. So, mathematicians, they don't like doing that. They actually, they like understanding for good reasons, understanding things intrinsically. So if you have a curve or something, they don't like to consider the ambient space, like the space in which it lives. We don't have a choice. Like we need the ambient space sometimes. But right, usually you won't see that. So what will happen in the course is that we'll only talk about like essentially plane curves, but the curve will going to live over another curve, not over a plane. We'll see. I mean, you don't see this number showing up at any point. We're just going to develop a theory and then apply it recursively as much as you'd like. Okay, other questions? I know it's still, that's part of the course. You see, I want to tell you stuff that I still can't, so. Okay. Like in 8 weeks, we're fine. 8 weeks, all your, okay. So, but the major questions, even if you accept the fact that, okay, we're going to look at these kind of sets as the evaluation points, the question that you care about, well, obviously, first of all, is how many, that's related to your question, how many FQ points do we have on this curve? I mean, at most Q cubed, of course, in this case, but how many do we have? I mean, that's going to be our N, right? Because we are going to evaluate it there. So definitely given a curve, and we want to understand how many points we are going to evaluate at. And the second question, which is not obvious from this description, is what is the genus of the curve? So at this point, it's not clear what a genus is, and definitely not why I care about it. But it turns out that this is going to be very much related to the rate of the code. Right? Unlike Reed Muller and Reed Solomon, where the rate was kind of obvious and the distance was non-trivial, here, first of all, even n is non-trivial. Like, how many points do you have? And then that's like a deep question. How many elements, how many solutions you have to an algebraic equation, right? The Diophantus or something. And then what's the genus of the curve is going to be related to the rate of the curve. Like, even after you know what n is, you don't know what k is. Like, okay. So there is some mysterious quantity. Actually, it's going to be demystified to some extent in like 4 weeks, but that is related to the code, and we care about it. And we are going to need to answer these 2 questions. The answer to the first question is Riemann's hypothesis for curves over finite field. That's a very, very deep question. Okay? And we're going to give the deep answer to it. And in order to answer the second question, which actually, it's kind of reversed. I can ask you this, but I can't even like meaningfully ask you what that question means, right? It's like we don't understand this question. But that question, even though it's easier to ask, is harder to answer. So this is going to be answered before that, even though we're going to formalize afterwards. And so as I maybe hinted before, the genus is going to be part of the Riemann's theorem. There is going to be a theorem, and it will tell you that there exists a constant that is invariant. It's a property of the curve, and that's going to be the genus. So we really have to prove Riemann or Riemann-Roch theorem even just to answer that. So these are very big questions, okay? And that's kind of amazing, right? To understand the rate and distance of a code, you have to like do so much. Questions so far? Okay. So have you ever heard about these things, like AG codes and stuff? No, never? Yeah. You see, well, people that do in AG and stuff, probably you don't have access to them because you're usually computer science, mostly, I don't know. And people, and they use it mostly for grants. It's an application of what they do. And we, like theoretical computer science, usually don't know that. We know it exists, but we don't know like much more than that. So yeah, good. We'll study it together.